Hi, folks. I want to take a little bit of time and review the things that you know about rotational motion. One of the things I love about rotational motion is how similar it is to translational motion. All the things we talked about with velocity and acceleration and momentum and energy have an analog in the rotational case. If it's possible for you to print out the translational versus rotational handout you see on the left part of your screen, that's a great resource. If it's not, take a piece of notebook paper and divide it down the center. You can use it to take notes the same way. Since we have linear motion and rotational motion, and they're so similar to each other, it's helpful to name what variables are analogs of one another. In linear motion, the first thing we started talking about was the position. We measured things' position in meters, how far something had traveled. In rotational motion, the equivalent of distance is angle, how many degrees or how many radians things have rotated. We then moved along in linear motion to talk about the speed at which something is traveling, how fast in meters per second. When we look at the rotational case, we will be looking at how quickly something is rotating. Our variable here is the Greek lowercase omega. That's that curly W thing. And the units we use are radians per second. How many radians is something rotating every second? In linear motion, we moved on to talk about acceleration in meters per second squared. How quickly is something's velocity changing? The rotational equivalent is the angular acceleration. That's the Greek letter alpha. It looks like a fish swimming to the left. Its unit is radians per second squared. How quickly is the angular velocity changing as something is rotating? Is it speeding up? Is it slowing down? In linear motion, the next topics we covered were things like forces, momentum, and energy. All of those relied on the idea of mass. Mass is the resistance of an object to changing its motion, or its inertia. In linear motion, we measured the mass in kilograms. In rotational motion, the equivalent is the rotational inertia. That measures how difficult it is to start or stop something from rotating. We give this the variable capital I, and we measure it in kilograms meters squared. In linear motion, we talked about forces. We measured forces as the amount of push or pull that has the potential to move something. We measured forces in newtons. Rotational motion, we have forces that may cause something to rotate. We call those forces torques. We use the Greek letter tau, and we measure torque in Newton meters. The last basic variable that we have is momentum. In linear momentum, we take the mass multiplied by the velocity, and we end up with kilogram meters per second. The rotational equivalent is the angular momentum, L. We measure that in kilogram meters squared per second. There are times when we need to go back and forth between the translational and the rotational motion of a particular object. This often happens if we're talking about a single point on a rotating object, or if we're talking about something that's rolling without slipping. In these cases, we use what we refer to as the bridge equations. Let's look, for example, at a point on a rotating object. Let's say this point, that green dot, is a distance r from the center of rotation. The rotation is happening in the counterclockwise direction at a speed, an angular velocity, omega. If we just look at that particular point, it's moving down and to the left with a velocity v in meters per second. The relationship between this angular velocity and the linear velocity is given by the equation here. V equals r omega. Similar equations exist for angle and for acceleration. Talking about linear motion, we had a number of equations that describe the relationships between some of our kinematics variables. We defined average velocity as the change in position over time, and the average acceleration as a change in velocity over time. These equations also probably look familiar from solving kinematics problems. All of these equations have a rotational equivalent. The average rotational velocity is equal to the change in angle over time. The average rotational acceleration is the change in angular velocity over time. And each of the equations that you see on the left has an equivalent with the rotational variables: omega instead of v, alpha instead of a, theta instead of x. After velocity and acceleration, the next topic you probably studied was force. Force is a push or a pull that has the possibility of changing something's motion. Rotationally, we talk about torque. Torque is a push or a pull that has the possibility of changing something's rotational motion. To calculate the torque on an object, we multiply the force applied by the distance that it is applied from the pivot point, or the lever arm. Torque equals Fr. When we talk about force, we also have to talk about the idea of inertia, or mass. Rotationally, the equivalent to mass is rotational inertia. The rotational inertia of an object is always proportional to its mass times its radius squared. And depending on the geometry of an object, its exact rotational inertia will be different. In the study of forces, we talked about Newton's laws. Newton's first law is that if the net force on something is zero, its acceleration will also be zero. Rotationally, Newton's first law says that if the net torque on something is equal to zero, its angular acceleration will also be equal to zero. Newton's second law tells us that the net force on an object is equal to its mass times acceleration. Rotationally, that means that the net torque on an object is equal to its inertia multiplied by its angular acceleration. If something is moving, we know that it has kinetic energy, 1/2 mv squared. But if it is rotating, in addition to moving translationally, it will also have rotational kinetic energy, 1/2 I omega squared. The conservation of energy is one of the fundamental principles of physics. It states that if the net external force on a system is zero, the total energy of that system remains constant. Sometimes we represent this total energy and the conservation of energy by using charts like the bar chart to the right. Rotational energy simply gives us an additional type of energy to add to our mix. One of the other fundamentally conserved quantities in physics is momentum. In the linear case, momentum, P, equals mass times velocity. In rotational motion, we also consider the angular momentum of an object. Here, L is equal to I omega. Both of these quantities are conserved, but they are conserved separately in any event. In the linear case, if there is no net force on an object, its linear momentum will remain the same. In terms of rotational motion, if there is no net torque on an object, the angular momentum of an object will remain the same. We look at this in several different examples. One example is when the inertia of an object changes. You can change your own inertia by moving your arms in or out. If your inertia changes, that means that your angular velocity will also change by the conservation of angular momentum. We also considered rotational collisions, collisions where an object may cause another object to begin rotating. In both of these cases, the conservation of angular momentum is key to solving the question. We've covered a lot in our study of rotational motion, but hopefully by drawing some parallels with linear motion, you've helped to put some of the ideas together. Happy physicsing!